Get your friends to dig your sig figs. It's how you show how much you really know. So sig figs, or significant figures, are basically how we report how much actual information that we know. How many digits that we report actually matter. Like if we divide 10 by 3 and we get 3.3333333, does that really mean that we know more than if we divide 10 by 2 and just get 5? So basically, if there are rules that we can use to know when numbers kind of matter and when to round where. And this depends on whether we're measuring values, whether we are calculating values. So if we're measuring values, then the significant figures is going to tell us about the precision. Basically, like how fine between the lines can we get? So if we say like 3.329, then I'm assuming that your measuring device has like 3.2 and 3.3. Those are actually marks, and then you're just estimating the 9. So when we measure values, then the last value is going to be like the estimated values, and the ones before are the ones that we're like sure about. So when it comes to combining like measured and calculated values, we need to be sure that we're rounding at the right places so that we're not like making it seem like if we measured something as being 10 and we measured and then we divided it by 3, now we're like reporting out that we have like a bazillion significant figures, then that makes the 10 that we had, like what's the significance of that? Like you lose your significance. And so you lose your idea of how good, like how much information you actually had in that original measurement. And so today I want to tell you about some of these rules that we use when we are calculating the number of significant figures, the number of significant figures we should have if we are measuring, if we are then calculating with those measurements, and also when we're reporting error. So when we're reporting, like we need to be rounding our error and then round to one significant figure and then rounding our data to match the error. And so this is like a huge pet peeve of mine, which is kind of how this post came about on a Saturday. So let's start more with like just what a significant figure is, and how we determine how many significant figures a number has. So if we're given a number and then we're asked how many significant figures does this have, all of the digits that are not 0 are going to be significant, but the zeros are where things get kind of tricky. And so let's go to an analogy and then some rules about this, and then we'll go into measurements, calculations, and error. So basically, a significant figure is a number that actually tells us something. So one way that you can think about it is if you have a movie theater and you're going to let people come into the movie theater and fill the rows from left to right. The first person comes in, they can just sit anywhere they want. But then after that, the people have the ability to sit anywhere in that row as long as it's to the right of the row. So if you imagine that the first person comes in, they sit anywhere. Their position, anything to the left of them isn't really going to matter because, well, it's not going to matter. So that's like if you have your first number's in the tens place, or it's in the hundreds place, or it's in the thousands place. The first digit, anything to the left of the first actual digit, so any zeros to the left of the first actual digit aren't going to count. Okay, so the next person comes in. Now they come. If they sit right next to that person, then they sat right next to that person, but maybe they sat one over. If they consciously chose to skip a seat, maybe that person smelled or something, then that empty seat is going to tell you something. So that's like having a 0 in between 2 digits. But what if the person sat directly next to the person, not because they wanted to sit next to the person, but because all the other seats were cordoned off? So if all the seats to the right were cordoned off, then sitting next to that person wouldn't tell you anything about them consciously choosing to sit there. So that's kind of like how trailing zeros, so zeros after your last significant figure, may or may not be significant, depending on whether they're like measured or calculated values, and that sort of thing. So let's go over some of these rules now that we have this analogy. Let's go actually with some numbers. So with significant figures, if there are, the biggest complicating thing is whether or not a 0 counts. And so if there are non-zeros on each side, that zero must reside. So basically, if you have a zero that's sandwiched by other non-zero numbers, then those zeros get to stay when you're determining significant figures. So if you had 101, that would have 3 sig figs. If you have 1001, that would have 4 sig figs. So these zeros are significant. But if your zeros are in the lead, erasing can proceed. So remember, this is like the first person coming and sitting randomly. So anything to the left of the first significant digit isn't going to be significant. But what if the zero is at the end? Well, then it depends. So if there's a decimal preceding that zero does have meaning. So basically, if there's a zero after the decimal point, then that's telling you that this zero is actually there for a reason, or else they would have just like left out the decimal point. And so these zeros that are after a decimal point are significant. However, remember that it's only the zeros, they have to have an actual digit, a significant figure before them in order to count. So like this one, this zero is after the decimal point, but it's not after a significant figure. So in this case, you only have 2 significant figures. What if there's a decimal at the rear, that zero you hold dear? So basically, if there is a decimal after a zero, then the zeros before that decimal count. And so in this case, you have 3 sig figs. If you had another zero after this, then you would have 4 sig figs, because like we saw before. Okay, if there's no decimal, but you had to round, confusion might abound. So if you had to round this, so you have 100, is this just 1 sig fig? Well, as it's written, you would think it was, but what if you actually had measured all of these values, or if it's an exact value where all the figures are significant, so like a counted value, so like 100 people, all 3 of those digits would be significant. But if you write it like this, it looks like you only have 1 significant figure. So in such a situation, turn to scientific notation. So with scientific notation, we can write 1 times 10 squared. If we have we want to use 1 sig fig, we can write 1.0 times 10 squared if we want 2 sig figs, or 1.00 times 10 squared if you want 3 sig figs. And so basically, you can write in a way that allows you to use the number of significant figures you mean to put. So this number of significant figures is going to depend on the number of significant figures that you want to include, that you want to report. Well, the number is going to depend on whether it was a measured value or a calculated value. So was it something that you actually went out and measured with a ruler or with some sort of scale or something like that? So basically, your scale is these are measured values. And so each non-zero number that you measure is going to be significant. But I'll talk to you more about how we make sure that when we're measuring, we make sure that we measure with the right number of significant figures when we're doing a manual measurement, as opposed to just looking at a scale. But your calculator is rounding off calculated values. With calculated values, we have stricter rules. There are also rules for when you're reporting error, and we'll get into this, so don't worry if these terms are confusing, but I just want to give people a little heads up about what's coming. And if you get one thing out of this, I hope you see this, because this is like a major pet peeve of mine, is that you need to be, when you're reporting error, that's like you're telling about like how unsure you are about something. And so you should only have 1 digit, 1 significant figure in your error. So if you're not sure about the first digit, you're definitely not sure about the second digit. And so then when you're adding this on to something, so the error is what's going to be after that, like plus or minus sign, you should only have 1 digit. And the digit of your error should match the digit of your data. So you should be rounding your data to match your error. Because if you say like 2.53 plus or minus 7, well, then that's this 5, like what's the point of this 5.3? Like it's just, you're not sure about this number. So you're really, really not sure about this number. So that's why we round it this way. And we'll get more into these things, but now let's step back and take things a little more slowly. So let's start with our talk about the measured values. So this goes to the issue of like precision. So basically, precision is how close together your measured values are, or how close together values are. And then like accuracy is how close they are to the actual thing. So when we're talking about like significant figures, we're talking about precision. So let's start with talking about measured values. So with a measured value, the number of significant figures is going to depend on your measuring device. So this can be your scale. So if you are using like an analytical balance, you're going to have more sig figs than you will with like a kitchen scale. If you are using a graduated cylinder or a ruler or a metric stick, in that case, your significant figures are going to be determined by the lines of the gradations of your cylinder, the lines, how close together the markings are on your ruler. So the basic concept is that you have to, all the values that you're sure about, so the values that are like lines, those ones are significant. And then you get one estimate. So you get to estimate in between them. So say you have a really competitive pin the tail in the donkey contest, and you're asking judges to measure where the how close the donkey's tail is to the actual thing. So you're going to read the lines and estimate between them. So you can basically say, okay, I'm sure it's between these two lines. And so I know it's somewhere between 2.5 and 2.6 centimeters, but I'm going to have to estimate how in between it is. So one of the judges says, okay, well, it looks about a fifth. I'll say 2.52. And then this other judge, it's clearly 2.53. Can't you see? And then the third one says, I say it's closer to half. So I'll say 2.56. So your judges aren't agreeing. But you have your values somewhere in this closer range between 2.5 and 2.6. Well, what if you have a meter stick? Well, now your situation is even worse. Now you can only tell between 2 and 3. So basically, your significant figures are going to be limited by your measuring device because you estimate between the millimeter lines in this case, but between the centimeter lines in the meter stick case. So when it comes to significant figures, when you're measuring, you're going to get the significant figures. You're going to have the digit. The last digit is going to basically be the estimated digit. And the digits before that are going to be the like more sure about digits. So now this gets to the case of, okay, well, what if we want to kind of talk about how sure about, what's the spread of those values? How sure are we about the values? How much are in agreement are they in the values? So there are basically this concepts of like error. So there's different types of error. So there can be like random error or systematic error. So if one of the judges was holding their ruler backwards or something, or more just like random ruler, these people just have a slightly different eyesight, or there's some glitch, I don't know. But basically there's different types of error that can lead to there being differences in the values. And there are different ways that we can report on this error, things like standard deviation, which is going to show us the distribution within a sample of the thing we're measuring, or standard error, which is going to indicate how representative a value that we calculate from a sample is of the overall population. Often this is done when we're using means, so like averages. In this case, we call it the standard error of the mean. But I'm not going to go into these things in this post. Stats isn't really my thing, but I do have a post on this. But in any of these cases, you're getting like a plus or minus thing. When you're getting this plus or minus thing, you're going to need to make sure that you're only keeping one digit in after the plus or minus sign. Because if the judges couldn't agree on, in our example, if the judges couldn't agree on like the 2, then they're not going to agree on the 0.5 after the 2. If they can't agree on this digit, then they're not going to agree on the digit afterwards. So even if you take the average of these and you were to say that, okay, well, the average has like, if you were to take the average of values and your value had more digits than you actually could report, well, then that's not very helpful, is it? Because that's not even like your device isn't even capable of measuring a third digit out here. So you shouldn't be reporting a third digit out here. And we'll get more into this when we talk about calculated values. But the basic idea is when we're talking about error, that if they're not sure about this one, then they wouldn't be sure about the thing after here. When we had this example, we could go out to 3 digits. But if they weren't sure about the second digit, then it wouldn't even matter if we had the third digit because we would have to round to here. So when you're reporting standard error, you're going to, or any kind of error, you're going to round to one significant figure in your error, and then round your data to match the decimal place of that error. So often this value that you're getting here for your value is going to be a calculated value. And so now we need to discuss what happens when we're calculating values. We have rules for this too. So if we're doing addition or subtraction, the answer should have the same number of decimal places as the starting value with the fewest decimal places. So in this case, we have 3 decimal places and we have 1 decimal place. So if we add these together, we're going to round to the 1 decimal place because that is the decimal place of the value. So when you're adding or subtracting, you round off your answer at 1 decimal place. However, when you're multiplying or dividing, here your answer should have the same number of significant figures as your starting value with the fewest significant figures. So you want to round, if you here you have 5 significant figures, but here you only have 2. So it doesn't matter that this one has 5. You have to go with the 2, and so you would round this to 53. So basically, when you're doing any sort of calculations, your value is going to be limited by the worst value or like the least precise value, the one with the least number of significant figures or the least number of decimal places. So it doesn't matter if I often get reminded of this when I'm doing my scintillation counting kinase experiments, and it's giving me these values with like 6 decimal places, or I guess not 6, but it's giving me these values with tons and tons of decimal places. And I know that when I'm doing my pipetting and stuff, I am not getting nearly that precise of measurements. So all of these values are going to get rounded down. So it doesn't matter that this machine is super duper sensitive because, well, when I'm pipetting, when I'm doing other steps, those can't be as precise. Speaking of doing these calculations, you want to wait till the end to round because where you round is going to affect things later. And because every time you round, but then you are like changing the value. Like if you were to round like 4.5 to 5 and then do calculations with the 5, it would be different than if you were to do calculations with the 4.5. Those little differences in rounding can add up and have bigger consequences. And so, yeah, so wait till the end to do your rounding. So let's look at a few examples. And so you can pause and like try to do it yourself if you want, or I'll walk through the examples. So basically, how many sig figs are there? And then what is the answer with the correct number of sig figs? So when we're just counting significant figures, so if we have 0.00908, the leading zeros don't count, and all the non-zeros count. And the sandwich zeros count. So we have 3 significant figures. And zeros also count if they're at the end. Zeros only count if they're at the end after a decimal place. So this would have 5 sig figs, and this would have 3 sig figs. And see here how we're doing this. We're doing it in scientific notation so that we can show that this 0 is significant. But if there isn't, if this was written like this, then we would only have 2 significant figures. So what about calculations? So here, if we're doing addition, or subtraction, it's going to depend on the decimal places. And so here we have 1 decimal place, we have 2 decimal places. So we go to the one with the fewest decimal places, and so we're going to round this to 5.5. In this case, this one has 0 decimal places, 1 decimal place. So we need to round to 0 decimal places. And finally, the division and multiplication. Here we go with the number of sig figs, the least number of sig figs, so 2 and 2. In this case, it's 2. And so we round this to 2. 2 and 1. Here we now need to round to 1. This would be ambiguous, but this is clear. And so with these, we're assuming that these are like not exact counted numbers. So not like saying, oh yeah, there's 2 people right there, in which case you would have like an infinite number of significant figures. There are also other values that are like conversion coefficients and that sort of thing. There are things where basically in that case, all would be significant. But when we're talking about like values that we have measured with our ruler or things like that, then we have to take into account the significant figures.